Welcome to this course on POS and digital electronics. In this first module, we will focus on the building blocks of digital circuits. We'll explore logic gates, transistors, logic families, timing parameters, and memory systems. These are the foundations upon which modern digital electronics, from computers and mobile phones to industrial systems, are built. Section 1: Logic at the device level. Digital electronics is based on binary logic, 0 and 1, low and high, off and on. These simple states are implemented using physical devices. Diode logic gates. The earliest logic circuits were built using diodes. A diode allows current to pass in one direction and block it in the other. With clever arrangements, you can form on and or gates. However, diodes cannot implement NOT functions on their own, which limits their usefulness. Transistor switches. The transistor revolutionized digital electronics. A transistor can act as a switch, either conducting current or blocking it, corresponding to binary states. Transistor gates. By arranging transistors, we can build complete logic functions such as NAND and NOR. These gates form the core of digital systems. MOS gates, metal oxide semiconductor devices, or MOSFETs, are widely used today. They have high input impedance and consume little power, making them ideal for large integrated circuits. Section 2: Logic families. Not all logic circuits are the same. Different logic families have evolved, each with its own advantages and drawbacks. TTL, transistor. A transistor logic. This was dominant for many years. It is fast, reliable, and relatively inexpensive. ECL, emitter-coupled logic, known for extremely high speed. ECL avoids transistor saturation. However, it consumes more power. IIL, integrated injection logic, a low-power family suitable for certain integrated applications. CMOS, complementary MOS, the most widely used today. CMOS offers high noise immunity and very low power consumption, making it perfect for modern chips. Each family differs in speed, power, voltage levels, and fan-out capabilities. Section 3: Performance parameters. When engineers evaluate logic circuits, they consider key performance metrics. Propagation delay. This is the time it takes for a change at the input of a gate to appear at the output. Fast systems demand minimal delay. Noise immunity. Digital signals may be corrupted by interference. Noise immunity measures how well a circuit distinguishes between valid highs and lows. Product terms. In programmable devices, product terms define logic combinations available in the architecture. We also find special types of gates such as open collector outputs, which allow multiple outputs to be connected together, and high impedance gates, which essentially disconnect themselves when not active. Section 4: Flip-flops, counters, and registers. Sequential circuits are at the heart of digital systems because they can store information. Flip-flops are bistable devices with two states, acting as basic memory elements. They are used in timing, synchronization, and storage. Counters are circuits that count pulses, used in digital clocks, timers, and frequency dividers. Registers hold data temporarily for processing. They are critical in processors, where they store intermediate results. Section 5: Memory systems and programmable logic. Beyond registers, more complex memory systems exist. RAM, random access memory, allows both reading and writing. ROM, read-only memory, stores fixed data permanently. PLAs, programmable logic arrays, allow designers to configure logic functions in a flexible way, making them useful for prototyping or specialized applications. Section 6: Data conversion and interfaces. Digital systems often need to interface with the analog world. Analog to digital converters, A/D converters, transform continuous signals, like temperature or sound, into digital form. Digital to analog converters, D/A converters, do the reverse, producing continuous signals from digital inputs, for example, in audio playback. Sample and hold circuits, S/H, maintain an analog signal value steady during conversion. LED and LCD displays provide human-readable outputs. Optically coupled devices isolate circuits while transferring signals, useful in noisy environments. Section 7. Operational amplifier applications. Op-amps are versatile devices, and beyond linear amplification, they can be used in digital context too. Comparators compare two voltages and output a logic high or low. Nonlinear applications of op-amps include precision rectifiers, oscillators, and switching circuits. Analog switches use op-amps or MOS devices to control signal routing electronically. In this first module, we introduced the device-level foundations of digital electronics, explored logic families, discussed timing and noise considerations, and examined memory systems, data converters, and display technologies. These are the critical components needed before we move to post circuits and timing systems in the next module.